Well, welcome everyone to our new year and the restart of our Advance-CTR machine learning series for health. Today we're really very happy to have Carsten Eickhoff, who is in Germany currently, but he's also on the faculty at Brown, to give us an introduction to deep learning, which of course is a very hot topic these days. And Carsten is the Manning Assistant Professor of Medicine and Assistant Professor of Computer Science at Brown. He leads the Biomedical Artificial Intelligence Lab here, specializing in development of data science and information retrieval techniques with the goal of improving patient safety, individual health, and quality of medical care. He is a prolific author, has published in lots of different journals and conferences. His research has been supported by many different funding agencies and large technical firms. He's also the founder and board member of several deep technology startups in the health sector that strive to translate technological innovation to improve safety and quality of life for patients. So really looking forward to Carsten's talk. And if you have any questions, we'll hold the questions for the end, unless Carsten wants to take them during the talk, but I'll let him tell you what he wants to do. But just put your questions in the chat and we'll monitor those and leave some time at the end for questions. So take it away, Carsten.
Thanks so much, Chris. And welcome, everyone. I'm very excited to be here, give the continuation on last year's talk, where we looked into an introduction to machine learning as a whole. And today I hope to go a bit deeper in figurative and literal ways to look at deep learning. All right, let's jump right in. So here's the agenda for what I prepared for today. So I want to do a very quick, no more than a minute, recap of machine learning. So really just, if you forgot everything from last year, here's the basics again. I want to talk a bit about deep learning to get you the general idea, how's that different from general machine learning, what's all the fuzz about, what are all these neural networks. I'll talk about one concrete example of deep learning architectures that looks at image analysis. And then I have two use cases that draw from deep learning. One that tries to do multimodal learning, where we use images and text and omics data for detecting Alzheimer's and diagnosing Alzheimer's in people. And then an unsupervised approach for dealing with heavily biased class distributions. So distributions where some classes are super frequent and others are very, very rare, which is usually not a great situation to be in as a machine learner, for diagnostic decision support. So really for primary care diagnostics, and especially how to not fold if you're looking at infrequent events, so rare diseases, for example. And then hopefully we'll have plenty of discussion. I have the question thread open here, so if any questions come up throughout, I'm happy to take them then, so I should be able to see everything. All right, let's jump right in. The very quick recap of what all this machine learning was about. And this is a year ago, similar time of the year, I told you if you forget everything and just remember one thing, make that these slides, and I'll bring you those slides again to see what's going on. So data is king. We need some of that in order to learn our machine learning models. Once we have our data, what do we do? And the very first step is usually we split this out into features, our observations, and labels, usually our outcomes, right? So the things that we want to predict. The next step is that we have some machine learning algorithm. So this can be as simple as a linear regression and can be arbitrarily complex. And we train that based on our features here. And what these things are trained to do is to predict other labels, right? So they see pairs of features and labels, and now if you give them just features, they'll predict new labels, right? So now we have this really nice mirror situation here of true labels that came with the data and predicted labels that our model spit out. And then somewhat unsurprisingly, we can now compare, right? We can really say, okay, for this data point here, you say 1, I say 0, that doesn't really fly. So how often am I right? How often am I wrong? That kind of thing. So that's our evaluation here. And we can just use this as a benchmark for ourselves and say, well, okay, we got 80% good, so that's great. Or, and this is where it all starts being magical, we can use this signal and feed that back into our algorithm, right? So this is this notion of training, where we say, okay, show me even more data points and I get a tiny bit better, and I make predictions again, and I check again for my predictions, how good are these now? And again, hopefully I get a tiny bit better. So, and this is being done via this vehicle of an optimizer. So a year ago, we talked about a bunch of ways of doing this, right? So we talked a bunch of ways how to phrase our problem in terms of features and labels. We talked about a number of machine learning algorithms. We talked a bit about evaluation, how to actually measure quality with these things. And we very briefly talked about optimizers. So all of this still holds. So that's the great news. So everything that we learned last year, we can reuse here. I'm just going to show you a few more techniques that are more specific to the deep learning world. And we're trying to do this in a quite unmathematical fashion. So I'm going to gloss over some of the mathematical details. I'll show you some numbers in order to make things fly, but we'll do this bite-sized. All right. So as the very quick motivation, I think we've all seen a million examples of where deep learning is touching, if not changing the world. But we have all kinds of systems that play a whole bunch of board games better than people could, or video games as well. We have all these image recognition examples of estimate my age or estimate my attractiveness or my whatever you want in an image. You've all seen these beautiful deep fakes of completely synthetic humans. You're aware of all the self-driving cars. So there's examples aplenty of where deep learning, which mostly is the case nowadays, where machine learning in the form of deep learning is around us and is doing good things, and sometimes not so good things. All right. What I want to look at first is how deep is this thing really, right? So what's really under the hood and how does all of this happen? So at its core, deep learning is really about abstractions of data, where previously we would say, okay, we handcraft these features and we really concentrate a lot on designing these features. Here, this idea is, can I learn these features automatically, right? And that's a very powerful paradigm here. It's trying to learn more and more coarse, maybe, or more goal-driven abstractions of data. Right. And in order to do that, these architectures typically end up being highly parametric. So I have a lot of degrees of freedom that I need to tune, right? So where our nice and well-behaved logistic regression might have as many degrees of freedom as I have variables that go in, these guys here might be in the millions or billions of parameters that I need to fit. That makes them more prone to overfitting, makes them very data hungry, and makes them computationally pretty costly. Okay. Yeah. Oh, okay. But really, if we're cutting down to the meat of it, all they are very complex function approximators. So all these things try to do is approximate some often unknown and not well-formed function. So something that goes from our inputs to our outputs. And this could be, for example, a very, very simple and not so super deep learning system. So I have two inputs here. Last year, we talked about height and age of a person or something like that, and we wanted to regress that person's weight, for example. And this might be what's going on here. So I have two inputs. I have a bunch of weights that connect these inputs with the next layer, right, in our hierarchical sequence. And the same thing happens again. So here I have these hidden units, these neurons in my network. And again, with a bunch of weights here, this is connected to my outputs. And these are the things that I'm predicting. And these things are strictly hierarchical. So meaning that the only way of getting from inputs to outputs is via these connections here. And I'm going to take you through one iteration of what we call the forward step. How do we make decisions? And then we're going to look at one iteration of the backward step. How do we get better, right? So there's this nice loop around where we try to optimize and make better decisions. Now, I give you here in red just some hypothetical values. So let's believe my inputs are 0.05 and 0.1, right? So some measured vital signs that I observed. in some data point, and I want to predict these two labels, right? So 1% and 99%, which might be likelihoods of outcome, right? So likelihood of complication, likelihood of no complication, or something like that. Just to make this fly, I'm giving you these here in red, these weights on all these connections here. Now this becomes the forward pass. This becomes a very simple multiplication and really a form of linear regression. So what I would do is I'm taking my 0.5 here, multiplying this with this weight, putting this here. I'm taking this guy here, multiplied with this weight, this connection here, right? Put this there too, and I add on both of these, this guy here, this 0.35. And this is exactly what your linear regression would do, right? So this gives me the value here. I can do the same thing here by taking this guy via this connection, right? 0.05 times 0.2 plus 0.1 times 0.3 plus again this guy here. So this gives me these values. I do the same thing here again, and I can calculate what's going on. So this, what we see here on the picture, would be just linear regression, but we could do multiple rounds of that. So if I add another layer in between here, right? So one more of these, I would have 2 rounds of linear regression and have many more. I can have non-linearities in here to make the whole function more expressive, but really at the heart of it, this is as simple as this gets. Okay. So this is how we go here. Now the backward pass, pretty unsurprisingly, goes the other direction, right? So I've made my predictions. I can compare with my ground truth label, right? So my ground truth is this here. So I know that this is what I wanted. And now I go backwards and I try to adjust the behavior of the model for the next data point. Okay. So if I do, so you'll have to believe me this because this is a bit iffy to calculate all these through, right? But if I carry these guys here through all of these weights, I'll eventually end up with these predictions here. So where I would have wanted 1% and 99%, what I get here is 75% and 77%. Not really brilliant, right? So this guy here underestimates the true label, and this guy here is way off, right? So this is much higher than what I would have wanted as my behavior. But, right, so this is noisy, this is not great yet, but it gives me something. Now I can measure. All right, so I can measure what's the distance here between these guys. I can measure this distance here, and I sort of get a notion of, oh, okay, how much course correction do I have to apply here? All right, and what I'm going to do is I'm now going backwards through, and I'm adjusting all of these weights here, these red numbers. All right, so I'm starting with these 2 guys here. And let's start with our O1, and our O1 here, my output is way too high. Right, so I want to make sure that next time I see a data point like this, the number that I'm predicting is hopefully lower. Okay, so this O1 here I can't change, but what I can change is the things that got me here. So it's these 3 weights, right? The 0.4, the 0.5, and the 0.6 here. So all of these I want to nudge a tiny bit. So in my case here, I want this number to be lower, so I make all of these guys a bit lower. Right? And we do this via some nice partial derivatives that we don't have to care about today. But so really just the intuition should be we just look at the direction of the error, right? Too high, too low, and we track this back through all of these weights. So we do this here, and then we do this in the next step. So for this guy here, we want to do the opposite. This guy we want to increase a bit, right? So this should have been 99%. I got 77%. So all of these weights here, right? This guy, this guy, this guy, I want to increase a tiny bit. And then we play another round of this here. So here it's a bit trickier because now everything corresponds to everything. So this guy had a bit of impact here, and I want this to be higher. But this guy also had a bit of impact here, and I want this to be lower. So we'll have to play some averaging and apply that to all of these edges that I have here, all of these weights at the beginning. All right, so on all of these net, I want to reduce just because I overestimated so much here and underestimated a tiny bit here. So net, I want to reduce quite a bit here. So, and this now lets me adjust all of these numbers a tiny bit. The next time this same data point or data point that looks a lot like this comes along, hopefully we get behavior that's a bit closer to 1% and 99%. And that's the whole magic. So this scheme here is called backpropagation. So we propagate the error that the model made back into its weights and into its behavior and thereby change that. We don't usually do this just a single data point at a time. So we use small groups of data points just to get a bit more robust behavior. But same game. So this is really what happens at massive scale. So remember, here we are having whatever this is, 10 weights, right? So the orange guys and the red guys. So tiny model. In reality, these are hundreds of billions, right? Trillions of parameters that I have to do this with. And that's what makes the training step, while your model learns, really costly potentially. Right? So this is the slow part of the whole machine learning business. Okay. So and now this gives us this nice paradigm of representation learning. So where in traditional machine learning, we would carefully design our features and learn a target function, and feature design often being more important than the actual machine learning algorithm. Now we try to jointly learn that. All right. So, and then often we can even use this hidden representation here in the middle and use this for other purposes. All right. So I want to show you, this was abstract. I want to show you one pretty concrete example of this at play for dealing with images. Many of you will have seen, so this figure is already quite a few years old, but I think it's still pretty instructive. And the whole idea is I feed this guy here at the beginning a whole lot of images. And so these are the pixels of the image. Right, so this starts out very broad because an image, of course, has many of those. And I learn over these connected layers to recognize basic shapes, to recognize maybe noses and ears and eyes. So the things that compose faces. Here, eventually, I have faces. Maybe here, I have the identity of certain people, and so on. Right. So in here, eventually, I make a yes/no decision. Are you male, female, or young, old, or whatever the taxonomy I care about? So that's the game that we want to play here. And I want to show you how this particular architecture, you'll have different architectures depending on the type of data you want to work with, right? So for text data, you will have different architectures than for time series maybe, or for images altogether again. But we'll talk about the image case today to just show you a bit how this works. Okay, so our first challenge here is an image is an image, and we can look at it and see cute kittens or whatever is on there, but computers, of course, can't see that. So our first challenge is how to make an image computable, machine understandable. And what we're going to do is we'll split this up into pixels and describe what is to be seen in a single pixel, right? So what color does this have? How dark or bright is it? Or what color do I see there? So if we, for example, take this cute picture here, this is what humans see, and this might be what the machine sees. So every pixel or every range of pixels here, let's say, becomes one number, right? And this could become a pretty large matrix here. So we could say this is maybe 20 by 20 if this has only 20 pixels square, and maybe it's 3 colors deep, right? So you could imagine that there's 3 colors stacked here on top of one another. So this is the computer representation. All right, that doesn't look like anything that humans want to look at. But I'll show you in a moment that even we can make sense of these. So and our goal here is to classify images, to recognize shapes, recognize maybe dogs versus cats in images, malignant from benign cancers, and so on. And our strategy is going to be we scan this whole image for certain shapes that we care about. So imagine this is our image in this numerical representation, right? So each of these little cells here being a number. And I have this group of 5 by 5, what that I call a filter, and I slide this over, right? I start here in the top left corner, and then I slide this way, and then I go down here, right? I really scan this entire image. I'm looking for a certain shape. And what I'm passing on to the next layer in this hierarchy is just how much of that shape did I see, right? Nothing of that shape, I pass on a 0. And then eventually maybe I'm here and I'm seeing 0.5 of that shape, right? So some evidence of a nose, maybe I'm putting on a 0.5, some noseness detected here, and so on. And this passes on to the next layer from pixels on this side, now something that looks for concrete things, noses that bear meaning and semantics, right? And I do this many, many times. So I start with raw edges and eventually noses, then faces, and so on. Okay, but how does this happen? Okay, so what does a filter look like? And like an image, our filters are, again, matrices of numbers. So let's imagine we're looking for this shape here, right? For some little curvy line. Then our filter would be something like this, right? So this would mean there's white up here, there's nothing, there's white again, there's white, there's white, there's white. There's a line here, and again, there's white, right? So I just put some values in here where I want this shape. And this shape here mimics that shape. Okay, so great. I have some locations of importance and all the rest I don't care about. Okay, and now we're playing this curve detection game. So this is our image. this is my filter, and this would perfectly match here, right? So this is great. So I recognize the backside of a mouse, which is a super important problem apparently in machine learning, finding the backsides of mice. How do we do this? This is the part of the image that I overlay right now with my filter, and this is my filter again. And all I'm doing is multiplication, right? So I'm taking the top left corner and the top left corner. I multiply these two guys, right? 0 times 0 plus 0 times 0 in the next cell, and so on, right? We play this game the entire way through. And now for this here, right, you can already see this guy here overlaps this guy here. So this gives me a few multiplications where I get my 30 times my 30 plus my whatever 50 times 30. So if I do this all the way to the end, I get a pretty large number, right? So there's a pretty large match here. If, however, I'm overlaying that same filter, so I'm still looking for the backside of a mouse, right? So this filter here, and I'm overlaying this over here, maybe with a bit of ear and face. You can see this is the ear, right? And this is the face here. There's a tiny bit of eye going on here. So now I do the multiplication again, and you'll see that there's no overlap whatsoever, right? So I have lots of 0 times 0. Up here, my filter would be looking for something, but that goes to 0 in the image. Here, I have a bit of mouse, but that goes to 0 in the picture. And overall, I get a 0.
Carsten, I have one actually. So
Yeah.
how do you know which filters to apply?
Right. So this really comes out of my my backpropagation magic again. So all I would say is, at this point, use 40 filters, and I'll leave it to the model. So these filters all are being randomly initialized. Right. So if I'm going back here, so all the pixels here, all the numbers in these filters here, I'll start with just random, right? So for each of these, I'll roll a die and put in some number between 0 and 100 or something. So they start out looking for nothingness, right? They're looking for random noise, and they're passing that on to the next layer in the network. And that eventually makes pretty poor decisions, because if everything's random, then my decisions of is this a human or is this a young versus old person is also really just random. But then I at least have a random decision, and I can play this game of backpropagation where I'm adjusting all my parameters, so every one of these little numbers here, to look for something that's useful. And my images will tell me, look, if you're looking for faces, you really need a nose, right? So eventually some of these filters will converge on things that look like generalizations of noses. And then somewhere else in the network, something like the shape of an eye or eyebrows or whatever else we have in our faces, maybe glasses, emerges as well. So this is really just something that we learn with the supervision of our downstream task of predicting maybe age or gender.
So in essence, the filters are just some of the hidden layers would be filters.
That's right. So the filters are part of the learnable parameters that we don't touch at all, which is really the magic of this. So if you had done image classification 15 years ago, you would have done SIFT features, and you would have carefully described, oh, look, if you want to do faces, then you really need eyes, and eyes can look like this and different colors and whatnot. So we would have painstakingly described this by manual features. And nowadays, we don't care. We really just say, here's a whole lot of pictures, and I tell you which of them have faces, figure it out. Which is really the magic of this, right? So this is, I think, where this representation learning, learn your features and then do something smart with it, why that is so exciting and why that's so much nicer than having to describe everything, think of every possible corner case in order to have a well-performing system. Awesome. All right. We're going to look into two concrete examples, and I think we should be good in time to do so. I want to start with multimodal learning. We're going to look at Alzheimer's detection in patients. And we want to do so. A lot of people performing machine learning, deep learning, whatnot, on clinical data will focus on a single modality. They will say, I have radiology output, let me classify this and determine who's ill and who's healthy or who has which disease, things like these. But really often we get a much more complete picture of a patient or of any data point really by looking at multiple modalities. Do I have a different view, a different angle on this data point that might tell me more than just radiology output is able to? So, and here we're looking at smart ways of dealing with multiple modalities. And this is work that has just appeared last week or 2 weeks ago in JAMIA. So I'm going to be quick on the health impact of Alzheimer's and why that's good to early on detect that, because it gives you much better progressions and much better outcomes if you spot it early on. There's been a lot of machine learning and deep learning work on this, but as I said, often we focus very much on one modality and don't really have this complete view on the problem. And in particular, what we are after here is modeling the interactions between modalities, not just saying, okay, here's a bit of image input and we'll learn something from that, and here's a bit of time series input or what have you, clinical values, and we'll learn a bit from that, and then we'll throw it all in one big bowl and see what happens. So now we really want to know, how do individual pixels of images interact with clinical findings and so on. So we really want this richness of interaction, which also downstream will give us much better explainability if I force my model to explain itself. Okay. So previously what you would see is something like this. So in our example here, we have clinical features that are observations from the EHR. We have genetic sequencer output, and we have imaging information. We encode this in some smart way. Many of these boxes here might be deep learning systems. And we take the output of these and just glue it all together. Right? We really just say, if we had maybe 10 numbers here that come out as an output and 10 here and 10 here, we'll make this thing 30 long, forget all about where this ever came from, throw this thing into a final classifier and get something. And that's okay, this works. But what we are proposing here is a system that allows for interactions between these modalities. So we'll have two forms of attention in these networks. This first form of attention goes between observations of the same modality, right? So basically clinical versus clinical. And then here we are mixing with the other two modalities. So this is blue, which is clinical with imaging, and clinical with genetic. And then for the other modalities, you see the same thing. And now that I have this explicit mixing here, I can really much more easily backtrack into, oh, these are explicit interactions between modalities, which is great, which is something we want. We ran a bit of comparison to previous work that did this here in slight variations, but pretty much this, and see that this works pretty well. So we have these different variations on 3 modalities, and we can see that we can do quite a bit better if we use something that has these explicit interactions between all of this. But then at the core of it, this is the same game that I showed you before, right? So I have my clinical data, I cast this into just numerical features. I have many layers of a neural network here to get to this blue representation. I have more layers of this neural network to get to this orange and blue mix representation. I glue this together, I have my output, and now I play this game that I told you about before, right? So I have all these inputs. I have my output that is predicted by the model. I have the true output, so I know who has Alzheimer's and who might only have mild cognitive decay and who might be completely healthy. And I adjust all these millions of parameters here. And really for this kind of model, we are really talking about probably a bunch of dozen million parameters. And adjust them every round of my game here to get better and better at this. And where you get is this, right? And this is pretty impressive if you again think about that there's no clinical knowledge in this, right? So never did any person say, oh, but really you should be looking for this, or you should be looking for that, or noses don't matter in looking for Alzheimer's, right? Because you're looking at MRI scans. So this is really completely from zero. So the only thing that you have is you have examples of healthy and diseased, and you get to something that's very close to a very well-trained physician. which is pretty magical. Even if we understand now how all of this works, I'm still very excited about all of these techniques here. All right. We wanted to see robustness of these different schemes here, and especially of what happens if we withhold some of these attention schemes. So the attention that runs within modality, the attention that runs cross-modality, and the combination of both. And we can see that sort of this combination of both really is not just in terms of absolute values, but also in terms of our confidence intervals here, our spread of the scores performs much better. So this was very nice to see. And then self-attention, so only attending to a single modality, so the stuff that everyone has been doing, really gives you this super wide range, right? You might be performing okay, but really you might also end up with something that's pretty poor. So it's risky business to bet only on the single horse, if you will. We did zoom in a bit on unimodal models. So these are models that really don't do any of this. They only say imaging alone, or clinical alone, or genetic alone. And remember, we got to 96 and a bit, right? So imaging gets pretty good. So if you have to pick a modality, imaging gets good, but this comes with the asterisk of gets good if you have a lot of samples. We played around with fewer numbers of samples, and then imaging completely fails because you are not able to train this model well. And then with combinations of modalities here, we saw this interesting effect, and you'll just have to take my word for it because these figures take a moment to unpack, where while imaging does best on its own, the moment you have two modality combinations, clinical is a bit of a gatekeeper. So clinical features really can boost your model even further. So clinical features were the most costly one to withhold from your two modality combinations. Which I thought was interesting to see. So clinical observations, in this case here, seem to help interpret either genetic or imaging input, even though imaging input is the big player. All right. So I guess as a quick conclusion of this very first project here, we looked at multimodal decision-making for classifying Alzheimer's in 3 classes, so healthy, diseased, and mild disease. And I think especially this role of clinical data and maybe imaging data was very interesting to see here. So we're excited. So where this project is going right now is really into a explainability kind of angle where we ask this model, okay, why do you come up with these decisions? Not just 96% good, but also really why this label for this particular data point, which is exciting and goes a bit beyond what you get out of your standard logistic regression, which can only tell you, oh, in general, pixels here are important, right? So this case-by-case reasoning is something that's pretty big. Okay, another quick breather. 1 application down, 1 to go. A good moment for questions if you have any. So the question here is, what tools are we doing to do this work? And are there any recommendations for beginners? So my lab works on a bit on an intersection of basic scientific insights. So we try to improve machine learning models in general, irrespective of application. But then we do have these concrete applications, such as maybe Alzheimer's now. So there's a bit of both. If you're after the fundamental improvement of machine learning, you'll end up using likely Python also as a programming language, and probably you'll end up with PyTorch as a library set, which comes with a whole lot of pre-computed models for you with architectures that you can import very easily. And really helps you do all the nitty-gritty details. If you're really only after a model that works, right? So you care not about the machine learning, but you care about the Alzheimer's, so to speak, then very likely still Python is your language to go for. But you have pre-trained models, you have a whole bunch of toolkits there that really give you more of an end-to-end. I don't want to say black box because that's sort of a negative term, but they really give you a a very easy stream towards models. So the keyword to look for here is either AutoML or super learners that try to just take away a bit of the engineering effort and just let you define inputs and outputs, and they try to automate a lot of the stuff in the middle for you. And we got another question, and I'm going to draw a blank on that one. What are the features in the clinical input? I have no strong idea anymore. So I believe the clinical features here were heavy. So this was broad. So this were 50 or 60 features, I believe. And they were strongly looking at cognitive exams. So tests that people have been doing now, some months ago, some more months ago. I think that was a very strong source of features that were in there. But I would have to go back and talk also with our clinical collaborators, because I don't know that angle too well. All right, good. And then finally, let's go into an application where I'm, after telling you a lot about deep learning, I'm telling you about how to not do it. So everything that we've talked about today was supervised, meaning that we have this nice feedback loop, remember, right? So this thing that happened on the right-hand side, where I look at model predictions, I look at my, my ground truth, and I use that for improving the model to make better and better decisions. Now, unsupervised learning doesn't do that. And I'm going to present to you a case for unsupervised learning. We're going to do some deep learning, but I'll show you how to maybe enhance it even further by doing something without supervision. Okay. Our practical motivation here is going to be diagnostics. So there's a lot of impact of diagnostic errors. So misdiagnoses are obviously a big deal. If I take too much time coming up with the right diagnosis, very likely the correct treatment is delayed as well, and maybe even delayed so far that the outcomes are worse than they could have been. And now the problem really is, if you think about rare diseases, things that don't occur frequently, they are often what physicians get wrong, because also physicians don't see them so much. You might not have them at the forefront of your mind because they never happen, right, so to say, until they do. And so often those are things that are misdiagnosed more frequently. So what we want to think about here is a world in which we have tens of thousands of diseases, all potentially could be presenting in every patient that you're seeing. And we want to use machine learning to help us make good decisions here. Now, this is a nightmare scenario for machine learners, right? We really like scenarios where it's healthy or diseased, right? So one disease versus no disease whatsoever. And I'll see 10,000 examples of this and 10,000 examples of that, right? That's where I want to be, right? Dogs versus cats, many examples, no questions asked, never lizards in any of the pictures. Now, here is sort of the opposite, right? So you have this super broad class hierarchy. There's 10,000s of classes. Some of them will be frequent, right? So diabetes, congestive heart failures, and others will be super rare genetic defects. And you may see 1, 2, maybe 0 training examples. So you might not ever have seen it in training, which makes it really hard to recognize them. So that will make supervised learning harder, right? If I have 0 training examples, I can't play this nice feedback game. And instead, we're going to rely on external knowledge sources such as PubMed. So the game we're going to play is, I'm not showing you examples, but you're allowed to read a paper about it, right? So I'm allowing my machine learning system here to go to the literature, read up on, I don't know, celiac disease, let's say. And even though I've never seen a celiac patient in my training cohort, I might have some chance of still guessing what's going on because I've read about this stuff, right? So that's sort of the metaphor that we're using here. Okay. I want to really quickly talk you through the data sets we're using. So we're using a pretty substantial chunk of PubMed, so 33 million paper abstracts. We're using UMLS, which is a structured thesaurus of medical language, to help us find canonical concepts. We're using the Mimic3 database, which is a de-identified snapshot of an intensive care unit. So this is, I believe, close to 10 years worth of Beth Israel Hospital in Boston's data, with pretty much everything in there that you would expect in an ICU EHR. So ICD codes, 15,000 unique diagnoses, 2,600 ICD codes, and so on, and like a whole bunch of things that are rarer. And when I say rare here, you don't have to think about true rare diseases as in weird genetic mutation, but really just things we don't see so often, right? So this might just be a broken hip. If that's rare in your data set, then that's a rare disease for me here. And then we're looking at a smaller data set of just 31 patients, but they're extremely difficult. So these are New England Journal of Medicine case challenges, where the whole community gets together and thinks about these odd cases that present very differently from how they normally would. Very, very briefly, what we're going to do is we're taking our patient node, we're filtering this for medically relevant keywords. We're going to sift through our literature, so through all of these 33 million papers, and trying to mine out of that a list of possible diagnoses, right? So which of these papers describe things that look similar to our patient here? So that's the game we're going to play. And this gives me a ranked list. So this is on rank 1, the thing that looks most like my patient. This is the thing that looks second most like my patient, and so on. And we do this for a very long list, potentially. Okay. And here's what we compare to. This is the game that I explained to you for the last 45 minutes. So this is a supervised model with millions and millions of parameters that does really well, right? And is being trained on all of these historic observations of here's a celiac patient, learn to say this is celiac. We have a bunch of models that are good at doing zero-shot classification. Zero-shot meaning this is this classification game where you don't have training data for some of the classes. And then we have this retrieval-based method, so this literature-based method that I showed you. And this is what comes out here. So here is the frequency of the diseases in our training data. We've seen one training example of this, between 2 and 10, 11 to 50, and so on. So from rarest to most frequent. And this blue bar here is the performance of our retrieval-based method. And this is compared, and again, look at this here, right? So this is not great. This is 12% correctness. But compared to these guys here that can deal with zero shot, right? So these models are all tolerant to being able to classify things that we haven't seen before. And we're going to run a tiny bit into our questions, but we should be fine here. Now, this is zoomed out, right? This is the same plot I showed you before with the blues here, and this is where the big guys play. This is the supervised model that we had before. So the guy that could really look at data and learn and train, and this is much better, of course. So here we get much, much better in making our predictions, but attention here we can't play. Right here, there's a single data point available, which is in our test set, right? Not for training. So there's effectively 0 training examples. I mean, this guy can't be there. And this happens, of course, for a lot of data points, right? So this is what we're trying to look at here. If we're comparing, our blue is our literature-based model, red is our big, bad supervised machine learning model, then we'll see that for everything that has between 0 and 2 examples available, our model is actually better than the supervised model. And then eventually this starts toppling. Okay. And then finally, that's good. Okay, so we now have an alternative to this, but it only works well if there's no data available. And so now what we come up with here is a combination. So we build a scheme where we say, okay, let's look at how frequent a certain diagnosis is. If it's very rare and I've never seen it, then I really want to trust the literature model, right? So then I kick my model and tell it, well, you know nothing about this, go read. And the model goes read and comes back with something. And otherwise, if this is diabetes and our local data set is very robust, so I've seen lots of training examples for this, I tell the model, just ignore the literature, you know all about this, just trust your gut and your knowledge. So we want to combine, hopefully, the best of both worlds. And this is also what we're seeing here. So orange in this one is the literature-based model, not so great on its own. Red is the supervised model. And blue here is the combination of both. And in most conditions, other than for things that are not being published on, so here now this is the frequency in PubMed, so things that appeared 0 times in PubMed, well, obviously we don't do so well. things that appear up to 100 times in PubMed, we already see improvements, and then 500,000 whatsoever times. So the more evidence I see in the literature, the more I can use this to help, right? And the more I see this blue combination bar of literature meets local knowledge, the more that works. And then interestingly, we see this work really well as well. So this is again our method here, and these are these zero-shot baselines on this data set of these New England Journal case challenges. So these are very different. So intensive care, pretty limited range of diagnoses, right? Because you have pretty much same by and large. And these here are all your wild genetic mutations. These are your strange presentations of the measles, but comorbidities in the game, and so on. And even here, so the way to read these guys here is that this is 1 over the rank of the correct diagnosis. So 0.3 means if I give you 3 diagnoses, the correct one will on average be in there, right? So if I give you, the physician, 3 things to think about, on average, you have the correct thing in there. Right, so this was the quick run through this example. My very quick conclusion of today, representation learning is king. So really this ability that we didn't have in traditional machine learning to say, I'm going to jointly discover the right features, the right way in which to phrase my problem, and the function to solve it. This really unlocked like this massive increase in performance. And this is really why 7-8 years ago, suddenly machine translation worked, right? If you used Google Translate before, you would get pretty weird rubbish. If you do it nowadays, you have to be very firm in these languages to do any better than machine translation systems. And this is really that difference between these 2 paradigms. At the core, it uses exactly the same principles as traditional machine learning that we looked at last year. So it's this same supervised game. But these models, because they are so heavily supervised, so many tunable parameters, they're very data hungry, and they can be brittle if you have small data sets. And that means as things get infrequent, like we saw now in this diagnostic example, you might simply fail, right? And that's why there's no single golden bullet. And for situations like that, you may want to play these ensembles, combinations of different models where you know, okay, this is my player for the rare stuff, and this is my player for the very frequent stuff. And with that, I would like to thank you for your attention. I'm very happy to take your questions.